For a long time, the blueprint for building a safe, autonomous vehicle seemed perfectly straightforward: write flawless, bug-free software. The core assumption was that as long as the internal code didn't crash, the vehicle wouldn't crash. But that logic ignores a crucial physical reality. A radar array or an optical camera can execute its programming flawlessly at a software level, yet fail entirely when struck by environmental triggering conditions, like sudden heavy snow. If a vehicle drives directly into the blinding glare of a setting sun, the camera isn't malfunctioning. It's functioning exactly to its hardware specifications, but the software behind it is suddenly blind, unable to interpret the washed-out data. To solve this, engineers adopted a different engineering standard called SOTIF, which stands for the safety of the intended functionality. Rather than simply asking, "Is the code broken?" SOTIF asks, "Can this system handle the unpredictable physics of the real world?" This philosophy shifts the engineering focus. Engineers are forced to look past the pristine internal software environment, focusing instead on how a machine survives the friction of a chaotic, unpredictable physical reality. To reach that SOTF standard, engineers use a strict 5-stage validation framework, expanding from the lab into reality. Stage 1 is bench verification. Engineers isolate hardware components on a testing table to measure physical limits, ensuring the machine's mechanical eye works perfectly. But an eye is useless without a brain to interpret the light it gathers, so the testing immediately shifts from the physical hardware to the software logic. This is Stage 2, algorithm performance verification. Engineers inject massive sets of pre-recorded data into the software to stress test its recognition logic. They measure exactly how accurately the algorithm categorizes shapes and places bounding boxes around specific objects. If a sensor passes Stage 1 and the algorithm passes Stage 2, you know the system works perfectly on a dark laboratory workbench. But that provides zero guarantee about what will happen once that delicate hardware is physically bolted to a 2-ton vibrating piece of metal. That brings us to Stage 3, vehicle integration verification. This is the moment the isolated system is forced to interface with the flawed reality of an actual car body. The specific angle and thickness of a windshield can instantly distort the optical clarity of a camera lens. Even the natural vibration of a running engine or the paint thickness on a bumper can severely degrade a radar's accuracy. Once the hardware and vehicle are communicating properly in the garage, the testing moves outside to Stage 4, test track verification, utilizing a dynamic, controlled outdoor environment. On a closed track, engineers can safely and repeatedly expose the vehicle to high-stakes nightmare scenarios. To see how the system reacts when a pedestrian violently slings out from behind a parked truck, they execute that run with a mechanical dummy. Finally, the vehicle graduates to Stage 5, open road validation. The controlled track is left behind, and the system is deployed into the unregulated public domain. The purpose of the open road isn't to test known hazards. Engineers use it to actively hunt for the unknown unsafe, the bizarre, one-in-a-million edge cases, like a sudden cloud of snow kicking up from a semi-truck, that human designers could never proactively script. These 5 physical stages build a vital foundation of trust in the system. Yet the open road reveals an infinite number of variables, proving that physical driving alone will never be enough to account for all of them. To prove a car is safe across every possible environmental variable, it would need to physically drive billions of miles through every specific weather and lighting condition on Earth. Because that physical requirement is a mathematical impossibility, engineers have to shift testing into the virtual realm, leaning entirely on massive-scale simulation. The innovation making billions of simulated miles computationally possible is the stochastic sensor model. Instead of rendering every individual photon of light, it relies on known statistical distributions to mimic sensor behavior, reproducing dropouts, noise, and physical flaws. By skipping the heavy physical rendering, these models allow for testing at immense scale. A server bank can run thousands of complex, highly unpredictable driving scenarios simultaneously, iterating through lifetimes of driving experience in fractions of a second. Autonomous safety is not a final destination, but a continuous loop. Physical road testing seeds data into stochastic simulations, and those simulations expose new vulnerabilities to test on the road, systematically reducing the chaos of the real world into a framework of measurable,